Today we're on page 4 of the chapter 1314 Chemistry 1 packet, and we're going to be talking about what we call two-condition problems. A two-condition problem is if you have a gas at a certain condition and you change it to another condition. So let's take number 1. Let's say you have a 2-liter balloon and there are 3 atmospheres of pressure inside it. So here's a 2-liter balloon, all right, and we have 3 atms of pressure inside the balloon. And then what we do is we make the balloon 1 liter. So clearly we're making it smaller. So we're cutting the volume in half. And then the question is, what do you think is going to happen to the pressure? So this is going to be a 1 liter balloon, and we want to know how many atms of pressure it has. So what we're going to do is we're going to design our formula with this general equation right here, PV over NT equals PV over NT. So pressure, volume, moles, this is moles, and temperature in the first condition is going to equal pressure, volume, moles, and temperature in the second condition. So let's pick out what we're changing. We're changing the pressure, we're changing the volume, we're not changing the moles, and we're not changing the temperature. So since the moles of gas in this balloon are the same as the moles of gas, the amount of gas in this balloon, N1, which we don't know, is going to be the same as N2. Even though we don't know what they are, they're going to cancel out on both sides. So we don't need N1, we don't need N2 because they're going to be the same. Then let's talk about temperature. We're not changing the temperature, so T1 is going to be the same as T2, and we don't need it. So now we're going to design our own formula with pressure times volume equals pressure times volume. Okay, so let's see how to do that down here. I'll keep it so we can see it. Okay, so let's design it. First we'll write P1V1 equals P2V2. Now we're just going to copy down our values. So the first volume was 2 liters. The first pressure was 3 atms. The second volume is 1.0 liters. And then we want to find the second pressure, which mathematically will come out to be 6 atms. So let's look at what happened mathematically and then understand common sense. We took the volume and we cut it in half, and the pressure then doubled, which makes sense. That's an inverse relationship, and we discovered that with our piston and book experiment. So you could see right here that it makes sense that if you take a balloon and cut the volume in half, the pressure will double. And mathematically you can see it from PV equals PV. Now let's try number 2. Number 2 says a balloon has a volume of 10 liters and a temperature of 30 degrees Celsius, and we want the new temperature if we're at 20 liters. So here's a balloon, and we're going to say that this balloon is 30 degrees Celsius, which is a little warmer than room temperature, 10 liters. And then what we're going to do is we want the balloon to have a volume of 20 liters. And we want to know what temperature is that going to be. Now the interesting about temperature is you always have to use Kelvin. You can never use Celsius. If you use Celsius in this chapter at all, just mark yourself wrong. It's going to be wrong. Sorry to say. So you have to change this into Kelvin. So remember we add 273, so this becomes 303 Kelvin. And now we're going to design a formula with volume and temperature. So you could see that volume is right here, temperature is right here, volume is right here, temperature is right here. Since we're not changing the pressure, P1 and P2 will be the same. The moles are also staying the same, so N1 and N2 will be the same, and we only care about volume and temperature. So we're going to do that down here. I'll do number 2 on the right side. So here's number 2. So we're going to design a formula V1 over T1 equals V2 over T2. So let's write the first volume was 10 liters, and the first temperature in Kelvin was 303 Kelvin. And then we know the new volume is 20.0 liters. And we solve for a new Kelvin temperature, and that's going to come out to be 606 degrees Kelvin. So that's the answer, 606 Kelvin. Of course, you could subtract 273 from that if you want to get the Celsius temperature. Just have to read the problem and see what they want. So subtracting 273 gives us 333 degrees Celsius. Same thing. Okay, so let's talk about common sense and see how this makes sense to us. Think about a balloon. If you want the volume of a balloon to go up by changing the temperature, you would have to make the balloon hotter. So if you want to double the volume, you'd have to double the temperature, and that's a direct relationship. And of course, that's the Kelvin temperature. So the final Celsius, as we said, was 333. So look, anything that gets multiplied in this formula is an inverse relationship. So P and V are inverse. Actually, N and T could be considered inverse as long as you keep PV the same. But if you divide, then they're direct. So V and T are direct, P and T are direct, V and N are direct, V and T are direct. Any dividing is direct. Every multiplying is inverse. Okay, let's quickly set up the last couple here. Now we're going to look at number 3. Number 3 says that we have a pressure in a flask is going to be 2 atmospheres, and it has a temperature of 20. Find the pressure at 30. So we're going to design our own formula with just pressure and temperature. So number 3 is going to be P over T equals P over T. Condition number 1, condition number 2. So let's just fix this. So what's the first pressure? 2 atmospheres. What's the first temperature? Got to change it to Kelvin. It's going to be 293 Kelvin because you added 273 to 20. Then we know the new the new temperature is 303 Kelvin, and we're looking for the new pressure, which if you do a calculator cross multiply, you're going to get 2.1 ATMs. Let's see if this makes sense common sense wise. We increase the temperature. What should happen to the pressure inside? Yes, the pressure should go up because again that is a direct relationship. Okay, let's go to number 4. This one is going to involve several variables. So this involves volume. Oops, I'm going to go to the blue here. This involves volume. This involves temperature. This involves pressure, and then a new volume if we have a new pressure and a new temperature. So now we're designing a formula with 3 variables, P, V, and T. So it's P1 V1 over T1 equals P2 V2 over T2. You're allowed to use any units you want as long as you use Kelvin for temperature. That's all that you have to remember is the Kelvin. Everything else you could just match the units and you're good. So the first pressure is 600 millimeters of mercury. That's a unit of pressure. We'll see and talk about that in class. And then the volume is 16.0 liters. And then this is 313 Kelvin. And then we have a new pressure of 500 millimeters of mercury. We have a new temperature in Kelvin of 323 Kelvin. And then we have to cross multiply to solve for the volume, and it comes out to be 19.8 liters. Lastly, we have a 24-liter volume, 9 moles of gas. We want a new volume with 18 moles of gas. So we're designing a formula with V and N. So V is on the top, N is on the bottom from our general equation. And when we plug in our numbers, we got 24 liters on the top. We have moles of 9 moles. And then we have 18 moles. And we have, mathematically, we'll get 48 liters after we cross multiply. So if you take a quick picture of this, you could see what happens. Here's a balloon. It's 9 moles of gas and 24 liters. But then if you double the moles, like you blow in more air, of course, the volume is going to go up. So that's a direct relationship, and it makes sense that if you take the moles and you put twice as many moles into a balloon, then the volume will go up, and that's a direct relationship. So all these equations have special names, the ones that we just did. So Boyle's law is with P and V. Charles's law is V and T. So you can remember Boyle's law alphabetically, B, C, and G for the first couple. The first one we did in class with the piston and the books was pressure and volume. Charles's Law, think of a Charles on television, TV. Think of your favorite Charles on television, and you can remember that's V and T. Gay-Lussac's Law is P and T, the only other two besides N that never got used. The combined gas law will combine all three of these. That's why it's called the combined gas law. So all these combined will make that. And then Avogadro's law you could think of, because remember 22.4 liters is 1 mole. We learned that before of gas at STP. So 22.4 liters for 1 mole. Avogadro's hypothesis was that equal volumes of gases will have the same amounts of moles even if they're different gases. So 1 liter of helium, let's say, had a certain number of moles. 1 liter of methane would also have that same number of moles. That was Avogadro's hypothesis.